Good morning. This is Dr. Jenkins, Dr. J, or good afternoon or good evening, or wherever you're watching this fine video from. This next video is hypothesis testing. This is a follow-up to our first video series, which was on types of research design. So, hypothesis testing is kind of the next logical discussion. But really, within hypothesis testing, there's so much more. We talk about alpha levels, p-values, type 1, type 2 error, all these good things. So bear with me. It actually might be fun if you give me a chance. All right, so as I said, this is a follow-up to the video series on types of research design. So you're a researcher, or you're stuck in a statistics class and you don't want to be, but you got to get through it. And you have a research question. You had a research question. So we already went through how to pick the correct research design. So let's say that you've chosen a research question and you've picked the appropriate research design. The next thing to do is to create a hypothesis and then go ahead and test it, which brings us to today's topic, which is hypothesis testing. But as Lee Corso says, not so fast, my friend. You just can't go off and run all namby-pamby and run a fly-by-the-seat of your pants study. There are rules, and if you don't follow the rules, the results that you get will be meaningless. And who wants to waste our time? Not you, not me. So, you have your question, you have your research design. Now we have to follow some very basic foundational rules of hypothesis testing. So if you read different stats books or other videos or whatever, you'll probably see hypothesis testing broken down into different numbers of steps. As you're going to see if I move forward, I've put together 7 steps of hypothesis testing. You might see it broken down to as few as 3, but whatever the numbers are, it's the same steps. So we're going to go through 7 steps of hypothesis testing, but really there's so much more inside, hence the party picture, because we are going to have some fun in describing all of these things. We'll try. Party! Because in this are so many foundational pieces that we have to understand. So we're going to go through such definitions as the ones listed here. Without further ado, let's just get started. So here we can see how I've decided to break down steps of hypothesis testing. And we're going to go through each one of these. Let's first think of an example. It's always good to use an example, I think. So I was thinking the other day, a good research question or hypothesis might be, my research question for this video series is enjoyment of hot dogs? Because why not use hot dogs? Is enjoyment of hot dogs greater at a baseball game compared to eating at home? And this probably is an A, then, when eating at home. Thank God I don't teach English. So for this example, our research question is going to be, is enjoyment of hot dogs greater at a baseball game versus than when eating at home? I tend to think I enjoy eating a hot dog more at a baseball game than when I'm just sitting at home, but this could be a good question to ask. So we're going to use this question as we go through. Okay, before we even get started, the whole foundation of this is that we're going to be using hypothesis testing for inferential statistics. In a future video, we're going to see the differences between descriptive statistics and inferential statistics. Descriptive statistics are basically to describe things. So descriptive statistics include mean, median, mode, frequency, those sorts of things. So if you want to find the average, Then we can do a descriptive statistic. But the next step up is inferential statistics. And this is probably what you're thinking of with statistics, a t-test, an ANOVA, things like that. These are inferential statistics. What it really means is, in inferential statistics, you are using a sample and you're testing that sample. So if I'm going to do my question and I want to know, is enjoyment of hot dogs greater at a baseball game versus when eating at home? I'm going to find a sample of people to ask them that question. Because it's really nearly impossible to get the entire population. How many people in the United States? 350 million. Is it really realistic for me to be able to test the entire population? No. So we fall to inferential statistics, where I'm going to take a sample of the population, and from that sample that I do test, I'm going to try and draw conclusions and, of course, make inferences about the whole population. That's why it's called inferential statistics. If I choose a sample that is representative of the whole population, then I can do that. Then I can just get a representative sample, test them, and make an inference to what would be true of the whole population. Just as an aside, sometimes it's rare, but sometimes you can test the whole population. Instances when you may be able to get all the data from the population would be if you're looking at GRE scores or SAT scores. Then you have like a national test bank where you can get all of the population data, but it's really rare. So most of our statistics in the real world here are going to be inferential. So if I'm going to be using a sample, well, how do I know if that sample is representative of the population? And that's where we get to our good old smiley face friend, the central limit theorem. Okay, if you were to look in a textbook, you would see the top definition for central limit theorem. I'm not even going to read it to you because I think it's kind of difficult to understand. So what I've done is, instead of just a textbook definition, I've put 3 basic points for what the central limit theorem means. If we have a large enough sample, then that sample distribution will likely be normally distributed. Everyone knows the bell-shaped curve. If I pick any dependent variable, let's see, what can be a good dependent variable? Height. If I look at height, probably if I take a sample, the distribution will look like this, a bell-shaped curve. The majority of people are going to fall into the same area. So maybe the majority of people are between 5'6" and 5'10", I don't know. And a much smaller amount of people will fall towards the ends. And that's what a bell-shaped curve means. It's a normal distribution. The majority of people tend to fall in the middle with smaller amounts of people at the ends. So what the central limit theorem is saying, if I have a large enough sample, then that sample distribution, the sample will be normally distributed. If I have a sample greater than 30 subjects, 30, 50, 100, 250, then whatever dependent variable I'm measuring will be normally distributed. In terms of math, there is a math component to this, and that's what I don't have in red because that's not the focus of this video or my stuff. The math does back it up. You're going to be seeing this word throughout today's talk, standard error. It's another way of looking at standard deviation, just a little bit different. But basically what this is saying is our sample standard error will equal the population standard deviation. Don't get involved in the math. We're just saying that whatever error is occurring in the sample is also going to be occurring in the population. But what really does this mean, aside from all that math? The central limit theorem. If we get a sample that is representative of our testing population, then we can use that sample data to make inferences to a larger population. That's the central limit theorem. Because if we get a large enough sample, the distribution will be normally distributed. If we get a large enough sample of people, we will have a bell-shaped curve. And if we can get that bell-shaped curve, that can likely represent the whole population. This is the foundation, ladies and gentlemen, of inferential statistics. If I get a sample of people that is representative of the population, that sample will likely have a normal distribution. The math is going to work in our favor. And all of those things put together means that we can get a sample, collect data from a sample, and from that representative sample, we can make inferences to a larger population, because that's really what we're doing all the time in inferential statistics. We're not able to measure the whole population, so we take a smaller sample. And if we do it properly, that sample will represent the population, and that we can make inferences from the sample to the population. Okay. As we're going to see later, and I'm just getting ahead of myself because I get so excited. We're actually, when we run a statistic like a t-test or an ANOVA, part of our testing is to make sure that the sample is normally distributed. So we tend to build in these fail-safes. So even though we assume this to be true, when we go ahead and run each individual statistical test, we likely just double check to make sure that it's normally distributed, our sample distribution. If not, we can sometimes make a couple of statistical alterations, or if it's really off, then we just know we need a new sample. Okay, let's get to the steps of hypothesis testing. We are ready, we're off and ready to roll. There's my buddy Usain Bolt, we're ready for liftoff. The first step of hypothesis testing is to create hypotheses. You can see that hypotheses, it's plural because we're going to make more than one. We're going to need to make a null hypothesis, which is a statement of no difference, and we're going to need to make an alternative hypothesis, which is a statement that must be true if the null is false. And then we're usually going to write it in symbolic form. But let's just give some example. Sorry about that. Still working on how to use this pen, as you can see. Oh, just got kicked off. There's my dog. Just got kicked off there. Let's see if I can go back to my presentation there. Love technology, right? Get kicked off. You see my dog. Now we're going to go back to where we were. Going to roll right with it. So we said we're going to create hypotheses. Let's just give some examples. In the example that we said, because I want to test, is enjoyment of hot dogs different at a baseball game versus when eating hot dogs at home? The null hypothesis means that there is no difference. So null means there's no difference. We tend to write these symbolically, and you'll probably see the good old-fashioned H. Usually H with a subscript 0 means null, and you'll see a colon. And we tend to use the symbol mu. Mu actually stands for population mean. Check it out. Even though we're going to be testing a sample, our goal is to make an inference to the population, so we can get away with using our symbol for the population mean. But if I was going to do this for my null, it would be the mean of enjoyment at baseball games is going to equal or be the same as the mean of enjoyment at home. So a null hypothesis, you're saying that there is no difference. In our example, there will be no difference in enjoyment of hot dogs at a baseball game, B, versus eating hot dogs at home. The alternative is going to be they're not equal. And if you're going to say they're not equal, we've got to write alternative hypotheses for every possibility. So typically you'll see this as H, maybe with a subscript 1. Maybe one of my alternative hypotheses is that enjoyment at baseball games is going to be greater than enjoyment at home. And that's what I think is going to happen. But you never know. So you have to create hypotheses for both. Then I would have a hypothesis number 2 that's alternative. And in this case, it would be that enjoyment of baseball game hot dogs is less than enjoyment at home. Perfect. So we have a null hypothesis, statement of no difference, then we have alternative hypotheses where there is a difference. Okay, the next thing we're going to do is we're going to choose a level of significance. And I gotta be honest with you, for the longest time, I didn't get this. And it took me a while to just break it down into as simplest of ways to understand it as possible. So let's try and do that. So you're going to see alpha set as, this little symbol. And for example, if I was going to actually run this study about hot dogs and enjoyment at baseball games versus at home, I would probably set my alpha level to be 0.05. As you can see in this little text box in the corner, 0.05 is the most common. But what on earth does that mean? And here's the thing. There's always going to be some possible error. No matter if I had the most controlled laboratory environment on the face of the universe, there's always going to be some error. Human error, error in the subjects, error in the equipment, error in the survey. There's always going to be some error. So because we know that no matter what, there's going to be some level of error, we set a level of acceptable error. And that's really what alpha is. So the alpha level is the level that we set as a researcher as an acceptable amount of error. A level of acceptable error. Maybe you like to see it in this way or this way, different ways to define it. The amount of error you're willing to accept and still be confident about the outcome. Or some people prefer to think of it the percent chance that your results are wrong. I tend to like to think of level of acceptable error, and an extension of that would be the amount of error we're willing to accept and still be confident about the outcome. As I said, I've chosen 0.05. If I were to make that a percentage, 0.05 is 5%. So if I'm going to actually run this hot dog test study, and I set my acceptable error rate at 0.05, that means that when I plug my numbers into the statistical analysis and I get my result, I'm going to be willing to accept that there's 5% error because I know that there's some error. So if I can accept 5% error, that means if I'm accepting 5% error, 5% is my acceptable error, that means that when I get my results, I'm 95% confident or sure that my results actually mean what I think they mean. So if I find that there is a difference in enjoyment of hot dogs, maybe I find that people enjoy hot dogs more at baseball games. After I run this statistical test, if I set my alpha level at 0.05, if my stats tell me that there was a difference in enjoyment, I can be 95% confident that there really was. And in many field studies, you accept a higher amount of error. When you're doing laboratory research, when you have more control, you can accept a lower amount of level. If you're doing medical research, say you're trying to see the effectiveness of a drug, you better have 0.1% error. But when you're in a research in a laboratory, you can control for more things versus if I'm out in the field, I can't control for as many things. You will see the alpha level set by the researcher. So if you read a journal article in the statistical analysis part, even before they get into the results, they'll say the alpha level was set at 0.05 for decision making. And that just means that that researcher said, okay, I'm going to accept a 5% amount of error. And that means that whatever results I get, I'm going to be 95% confident that these results are actually true from this sample. Level of acceptable error. Okay. So we keep going. So far, we have our hypotheses about hot dog enjoyment at baseball games versus at home. We've chosen our level of significance, which means that we have a 5% level of error that we're willing to accept, which means that we're going to be 95% sure that the results that we get are accurate. Now, you're going to create your sample and run the study. Obviously, that takes a long time. In today's video, we're going to be flying right through it. Oh, if only it were that true in real life, but it's not. But today's talk is more about the foundation of our statistical inferential tests, so we're going to breeze right through it. Look at that. In this amount of time, we've already gotten our sample of people, talked to them about enjoyment of hot dogs, and now we're back and ready to go. So step number four, after we run the test, is to create a sampling distribution. We're going to go through this completely, and you may be giving me a look like this little cute baby is, but I'm telling you, it's really important, and I am here to help you. We're going to break it down. You're going to get it. I've just talked about this already, but these steps of hypotheses testing, this is the foundation of inferential statistics. This is the visual basis. This graph in particular is the visual basis of running a scientific study using inferential stats. It's so important to understand conceptually. When you're actually doing a real statistical test, you get your data, you plug it into SPSS or whatever program you're using, t-test, ANOVA, whatevs, you're not going to do this. You're not actually going to write out this distribution curve. But while you're learning statistics, it's also important to understand. If you're in my statistics class, for example, you will be having to write this out just so you can understand what's going on. So we're going to write it out. Okay. Create a sampling distribution curve. Let's get my trusty little pen going. So we've already established that if we have a large enough sample, I'm terrible at drawing bell-shaped curves. It's always longer on one end than the other. We've already established that if we get a big enough sample, that means that our sample distribution is going to be normally distributed, a bell-shaped curve. So we know that. Okay. The first thing that we would do if we were going to actually create this sampling distribution is we're going to add standardized scores. In the previous slide, and you can go back and forth and pause this if you'd like, but if we were actually going to assign standardized values, typical standardized values include a z-scale. Sometimes you'll see it as different letters, but we're going to just use z-scale. We'll talk about this more later. But the point of a z-scale is that it is standardized. The center of our z-scale line here is always going to be 0. This is a standardized scale. This is a concept that's going to come up again and again. Within an actual statistical test, the units of your dependent variable are going to be different. If I'm giving a survey about enjoyment of hot dogs, maybe it's a Likert scale, and I get an average out of 0 to 5. 0 means no enjoyment, 5 means the best enjoyment possible. So a mean score of 4 tells us something. If I'm measuring vertical jump height in athletes, maybe the vertical jump height is in inches or centimeters. If I'm assessing blood pressure changes over time, the unit in blood pressure is going to be millimeters of mercury. So between different tests, you're going to have different units of whatever it is you're measuring. Because of that, you cannot compare those units. If I want to compare significance between different tests, how could I compare inches to millimeters of mercury? You can't. So one of the tricks that we use in math and statistics is to create a standardized scale where we're able to convert our actual units into a standardized value. So no matter what unit you're looking at, I could compare across multiple different studies of different dependent variables. Or even within the same test, within the same study, you may be looking at different dependent variables. If I'm doing a test about blood vessel health, I may be measuring blood pressure, I may be measuring arterial stiffness, and they have different units. So even within the same study, a standardized scale is very important. So on our distribution, on our bell-shaped curve, we're going to, at the bottom, put our standardized units. And then we're going to be using plus or minus standard error. I'll talk about standard error later. You might see this and think that it looks like standard deviation, which in some ways it's similar, but a little bit different. But suffice it to say for now, if I have my standardized scale, I could say that's at 0, was right in the middle. 0 would be the mean or the average of all my scores. And then as I move further away from the center of the bell-shaped curve, I have more error, or I have more deviation from the mean. Okay, after we put in the z-scores, then we can add our raw scale. And we add a second scale, because if I'm drawing this out conceptually, I care about my standardized scale most, but I also might want to put whatever unit I'm working in. So if I'm doing the raw scale, maybe that's going to be the specific unit of whatever it is I'm measuring. If I was doing enjoyment and I was doing of hot dogs, and it would be a Likert scale 0 to 5, maybe my raw scale would be on units from 0 to 5. In the middle, we're going to have our mean. Let's say that the mean of all of my scores, because remember, we've already ran this study just like that. Let's say my mean was 3.5. So on a Likert scale of 1 to 5, the mean enjoyment of hot dogs was 3.5. And then whatever the standard error was, we can fill those in. Maybe it was a low standard error. So that means that maybe it was only 0.5 plus or minus. So that means that this would be 4, this would be 4.5, and this would be 5. Again, don't worry about this so much now, because we're going to talk about this more later. But the key points to get here is I have my normal bell-shaped curve, and we have a standardized scale that can be used across all units. And for sake of understanding, if I was to draw this out, I would also be drawing out my raw numbers. Okay. The next thing you would do is we're going to have to separate the critical from the non-critical regions. And we're going to get this from a critical value. And I've given you some examples. If you were using a t-test, I would go to a table and I would look at critical values for t-tests, t-scores. If I was doing an ANOVA, then we're talking about f-scores, and this would be my standardized table for f-scores. Or if I'm using z, then I would use this one. So basically, the next step would be to find your critical value. And you would do that by going to a table that already exists. So after I set up my normal distribution curve, I have my standardized scores at top, the z-scale, and then I have my raw scale with my actual units. The next thing I'm going to do is I'm going to, depending on what test I'm using, z, t, or f, I go to a table that's already out there. And based off of my set alpha level. If I was using an alpha level of 0.05 and it was a two-tailed test, I would follow, this z-scale here is actually a one-tail. So if I was doing an alpha of 0.05, I would do that, and I'd come across to my actual z-score, and I would get my critical value. We're going to talk about this much more later. Just know that the next step would be to go to a table. And using the alpha level that you set, you're going to get a critical value. So we set our alpha to be 0.05, our acceptable error rate. Right. So let's say that I get my critical value, and my z critical value from the table is, let's see, what kind of critical value can I use? Let's do 1.96. Depending on whether you're doing a t-test or an ANOVA, it's usually going to be somewhere between 2 or 3. This is close to 2. Okay, so let's say that I get my critical value. Then I'm going to draw that in. My critical value for the z, so I'm going to use the standardized scale, is plus or minus 1.96. That's going to fall pretty close to the 2. Plus or minus 1.96. Okay, so you find your crit value from a table, and then you draw in your crit score. And that's going to be my Z crit. Look, I changed to red, because crit means critical. And the last thing we would do, because now we have our critical values, now I can put in my critical region from my non-critical region. What's in between, change to blue, what's in between the critical now becomes the non-critical region. And what that means is, let's go back, maybe I'll pick red for the others. That means that whatever is on this side, I don't know how it keeps changing color. I'm going to have to fix that. If the middle is non-critical, whatever is on the outside ends of the Z crit are our critical regions. I know we just covered a lot, but you can review it. The steps are the same. So this is a visual conceptual basis. Because we know the central limit theorem, we know that our sample distribution is going to be normally distributed, a bell-shaped curve. Great. Now we're going to have a Z scale, which is a standardized scale. Because we have different units across the same test or different studies, we need to have a standardized scale so we can compare everything, no matter the unit. So we tend to use a Z scale, where the middle of our distribution, or the mean, would be 0. And then I can go plus or minus to either side with the errors. At the same time, underneath our standardized Z scale, I can do a raw scale. And these are actually in the units of whatever you're looking at. Our example was enjoyment of hot dogs on a Likert scale 0 to 5. So my mean, if I run my sample, my study, my mean enjoyment was 3.5. So I line that up with the mean of 0 of my standardized scale. And then I go to the size, plus or minus whatever standard error I get. Next thing I did is I go to a known table. And I pick, using the alpha level and the appropriate statistic I'm using, which we'll get into later. But you go to a table, you get a critical value. Let's say that my critical value is 1.96. So I drew lines at plus 1.96 and minus 1.96. Whatever falls in between those critical values is now known to be the non-critical region. Whatever falls to the outer edges of those critical values is known to be the critical region. This is the hardest part of this. You can get it, I promise. Okay, so we've created our hypotheses, we've set an alpha level, we've run the test, and we've set up our distribution curve. Now we want to see what our results are. What did we get? In the previous slide, we found our critical value. This was from a table, right? Nope, wrong one. We had our critical value from a table. So I want to point out that the critical value is different from our actual obtained. Quite a few things to unpack here, but let me help you. We can combine these next two steps together, calculate the p-value and fill in the rest of the distribution curve. So I'm going to be bunching these two together. This is a picture here of what we just drew, right? My raw scale, my Z scale and my raw scale. The values in the raw scales are different from the values that I put up there, but we would just know that the Z scale is a standardized unit, or standardized scale with no unit, and the raw scale is an actual unit for whatever we're measuring. Then we put in our critical value, and we can see the critical value is what I said it was. All right, come on now, pen, you can do it. There we go. This was our critical score, 1.96, critical. Before we get into p-values, let me just tell you that we already found our critical value Now we're going to actually run the statistics, and we're going to get our obtained. Really important difference here. So we already have our critical value. Oops, keep pressing the wrong button there. Okay, we already have our critical values on the scale. But once we run our tests, you're going to get an obtained value. If I run a t-test, my t-score might be 27.2. If I run an ANOVA, my f-obtained, my f-score might be 3.75. So you can plot your obtained one. Let's say that I run this as a z-test, because you can do that. And my z-obtained, right? My z-obtained was 27. So if my z-obtained was 27, I run my statistic using SPSS, and it spits out a number. I can compare and plot my z-obtained. So I would use the bottom, which is the unit, the raw scale, and on these scales, if I got 27, then it would be out here, right? So that's my z obtained, and it's very important that you label it properly. We had our z critical, which was plus 1.96, and then I have my z obtained, which was 27. If I follow this down, a z obtained of 27 here, what does that mean in my raw scale? Maybe on the raw scale, my z obtained is plus 2.4, right? If my raw score is 27, right, falling between 26.6 and 28.4, if I just move that up, I don't know, to me that looks like it's about plus 2.4. So you can write your z obtained in the raw scale and also the z scale. You compare your z obtained to your critical value. So whatever test statistic I get, z, t, f, whatever test statistic I get, I compare it to the crit. And then I look, does that obtained value fall in the critical region or the non-critical region? If I look at this one, it looks to me like, let's go to blue. If I look here, I'm in the critical region. What if, let's do it this way. Maybe this will allow me to change colors. Let's go back to red. What if my z obtained was 24? Then my z obtained would be there. And that would be a raw score of maybe 0.4. So if my z obtained was 24, I would then fall in the non-critical region because it's between these two here. All right, so what you would do is you're going to plug your numbers into your SPSS software or whatever program you use, and you're going to get a z obtained. You plot your z obtained, and then you see whether the z obtained or t obtained or f obtained falls within the critical or non-critical region. And oh, by the way, how did we determine what the critical and non-critical region was? By our critical values. So if I go back, we set up our z-scale and our raw scale. We went to a table to get our critical value, and then we plotted our critical value. After plotting the critical values, we could set up a zone that was a critical region in the middle, and then on either ends, non-critical in the middle, and then either ends were our critical zones. So that way, when I get my z or t or f obtained, I can clearly see whether it falls in the critical region or the non-critical region. Boom. Now, we're also going to get a p-value. So if you're in a statistics class like mine, I'm going to have you do all this stuff. And you're going to hate me, but it's a way for us to understand what's going on behind the scenes. But to be truthful, you really don't have to plot this out every time you run a statistic. Because when I run my statistic, t-test or ANOVA or whatever the case may be, it's going to give me a p-value. So I don't even have to draw the distribution curve. It's going to give me a p-value. And that's really all you need. But of course, we like to understand things better. What I've given you here are two examples of how you might see our statistical results written. Because it's showing me an F, I know these are ANOVA results, which we'll talk about later. And then the numbers beside it are degrees of freedom, 5 and 12. We'll get to that later. But if I were just to look at, let's say that I look at an article and this is what the results are telling me. And you're like, what the hell is that? Well, it's ANOVA results. And the F value, this is the F obtained. So if I were actually doing this by hand, my F obtained would be 4.51. And I could literally plot that on the raw scale, because those will be raw numbers, which actually don't match with these raw numbers, but that's okay. And then beside the actual F obtained value, it gives me the P value. And let's talk about what the P value is. The P value is the actual level of error you got in your analysis. We went back to before the alpha level. Remember we set the alpha level ourselves? So if we're doing our hot dog example, the alpha level was our acceptable amount of error. So we set our alpha level to be 0.05. That means that the acceptable amount of error that we're willing to accept is 5%. In other words, I'm going to be 95% sure that the results I get are accurate. So this is our level of acceptable error we set, the alpha. But then we run the analysis and we get an actual level of measurement. And that's what a p-value is, the actual level of error. So the p-value in this example is 0.04. So what you do is you compare your actual level of error, you compare the actual amount of error that you got, the P, to the level of error that you set to be acceptable. So I compare my P to my alpha. Check it out. If I got P equals 0.04, my P is less than the alpha, because in this example, the P that I got was 0.04. The actual error I measured. The alpha level that I set was 0.05. If my actual error was lower than the acceptable error I set, error is low, we can trust our results, we reject the null. So if my actual level of error is less than my acceptable error, then my actual level of error is less than the acceptable error I set. So I reject the null. Versus, what if my p-value up here, what if it was 0.08? If my p is higher than the acceptable error. So if my p is greater than the acceptable error, I have more error than I said I was willing to accept. If my P is higher than the alpha, if my actual error is greater than the acceptable error I said I was willing to accept, error is high, there's too much error, and I have to accept the null. Oh man, I know this is not that sexy when we talk about steps of hypothesis testing, but in terms of understanding the foundation, this is really the foundation of inferential statistics, and I am excited about it. So this leads us right into our last step, determine whether to accept or reject the null. We can accept or reject the null using our p-value, or we can accept or reject the null by knowing whether we're in the critical or non-critical region. So we can determine whether to accept or reject the null through two ways. And we actually already talked about these, didn't we? because I said here we can plot our obtained statistic and see whether it falls in the critical or non-critical region. Or I could just look at my p-value, which is the actual error value. So here are those two ways to do it. One way to do it by hand is to plot my obtained value. Let's say that my z obtained was 2.64. If my z obtained is 2.64, and I plot that, and I already know where my critical value is, my obtained score is to the critical region side of my critical score. So this means that I'm in the critical region. If I'm in the critical region, I reject the null. So if this were my hot dog analysis results, I would reject the null. And rejecting the null, because remember, what was our null? Our null was that there was no difference between enjoyment of hot dogs at a baseball game versus at home. If I reject the null, I'm saying that that's not true, and there actually was a difference. So if I reject the null, I would have to choose the alternative. Let's try that again here. If I reject the null, I would have to choose the alternative. And if I wanted to see which alternative was true, whether enjoyment was greater at those in baseball games or enjoyment was significantly greater at home, I could look to see on which critical region I fall, on which side. So that's one way to do it. Or I could just look at the p-value. So let's say that I got my results and my p was 0.04. Remember? What if my p was 0.04? If my p, that's the wrong one again. If my p was 0.04, that is indeed less than the acceptable error rate I accepted. So my actual error was less than my acceptable error. That means that error is low. I can trust my results. We reject the null. So they're both telling me the same thing. To the right, I was in the critical region. I reject the null. My p-value was less than the alpha. I reject the null. And by rejecting the null, I have to accept one of the alternatives. Of course, the opposite could be true. If I was doing my distribution curve and my obtained score was in the non-critical region, if you were in the non-critical region, you'd be forced to accept the null. On the other hand, if I was looking at the p-value, if my p-value was too high, I mean, sometimes we'll get p-values that are really high. What if I get a p-value of 1.8? Woo, my p-value was much higher than my acceptable error. Remember, p is the actual error that you got. So if I compare my actual error to what I said was acceptable, and my actual error was much higher than what I said was acceptable, I have too much error. And because I have too much error, I really don't know whether the results were accurate or not. I had too much error to really determine whether or not there was a real difference. And in that case, you would have to accept the null. All right. There's one last thing to talk about. Oh, man. You thought the fun was over, but it's not. There's always still room for error. Damn it. Remember we said the alpha level? We set an acceptable amount of error. Commonly, in real-world studies on people, your acceptable error, your alpha is 0.05. That's 5%. So 5% error means that I'm 95% confident that I get my results are accurate. If I'm 95% confident my results are accurate, I'm still 5% confident that my results weren't. So even if I ran my statistics well, and I may be under the acceptable statistical error, even if I'm under the alpha, there still can be errors because I still have that 5% of error that I said was okay, because sometimes it happens. And sometimes that results in us coming to the wrong conclusion. So even if I get my P level, let's say my actual error was less than 0.05. Statistically, I would say, oh, my results are significant, yay. But there still could be error, and that could lead me to the wrong conclusion. And there's two types of errors to look out for. Oh, got kicked off again. Got to see my dog again, but we're almost done. I mean, this way we get to go back and see all the fun that we've done. I don't know why it's doing that. All right. There's two common errors, type 1 and type 2. And I'm sure you've probably heard of these, and there's different ways that people can define them. I try to keep it really simple. So type 1 error, anytime you reject the null when you shouldn't have. Type 1 error is when you reject the null even when you shouldn't have. So this is basically when you concluded there was a difference, but in actuality there really wasn't. Some people will call this a false positive, where statistically it said there was a significant difference, but in actuality there wasn't. So you rejected the null and chose the alternative even though you really shouldn't have. In the hot dog example, if I were to do the study, enjoyment of hot dogs at baseball games versus eating at home, and I found that the difference was significant, there's a chance that I made a type 1 error. There's a chance that I found statistically that the things were different, but in actuality, there wasn't. There wasn't a difference. Maybe the sample that I chose wasn't representative of the population. So what if, for my hot dog example, what if I chose to look at only men between the ages of 40 and 60? If I chose my sample to ask about hot dog enjoyment and I only used men between 40 and 60 years of age, it might show that there was a difference, that they enjoyed hot dogs more at baseball games than at home. But there actually may not be a difference in the population. Why? If I think about baseball fans, they're probably mostly males 40 to 60. What about everybody else? What about males and females 18 to 39? They probably don't watch baseball as much. So I found the difference only because I chose a poor sample. So that could be an example when I would make a type 1 error. A type 2 error is when you accept the null when you shouldn't have. This means that you said there wasn't a difference when there really was. Sometimes people consider this to be a false negative. You said there wasn't a difference, but there really was. In my example, maybe I just had a low N. Maybe I only looked at 20 people. So maybe in my 20 subjects, there was no difference in enjoyment of hot dogs. But if I had chosen 100 people, I'm more likely to find a difference. Just more people, more likely to be representative of the population. The only way to eliminate both type 1 and type 2 errors is to have a huge sample size. So in terms of research design and statistics, one of the best ways to avoid these types of error is to just have a really big sample size, which isn't the easiest thing always. But the more people you can test, the more likely you're going to be having a normal distribution, and the more likely you are to limit type 1 and type 2 errors. Okay, that's everyone. That's it until next time. Steps of hypothesis testing done in the books. Here's a nice cartoon for you. I will see you next time.